Hi everybody, this is Mike Mancillas with Electrical Engineering 140. And we have a problem with two concentric spheres with radiuses A and B as shown in the figure. The inner sphere carries a uniform charge density ρ equaling alpha, and the outer shell carries a non-uniform charge density of ρ equaling negative beta r, where alpha and beta are constants. Our task is to find the magnitude of the electric field in the outer shell between the radiuses B and A. So whenever you have a problem like this, the E field is coming out the same in all directions, and it has a lot of symmetry in the problem. So whenever there's symmetrical problems like this, you want to use Gauss's law. And Gauss's law states that you have some integral of a closed surface, and you're finding the E field by plugging in some, surrounding it with some Gaussian surface, and that's going to tell you what the enclosed charge is divided by the permittivity of free space, your epsilon naught. And to explain what this integral is telling you is that if you have some charge Q, some positive charge Q, it's going to have an E field that's radiating outward in all directions. And we were to surround that surface, that charge, and let's say you wanted to know what the E field was at some point r away, then you could make some kind of Gaussian surface around that point, or that encompasses that point and surrounds your charge, right? And since you're taking the integral of this, that just means you're breaking up this surface into a bunch of tiny pieces, and I notice that this integral has a dot product in it, and we can make this a lot easier. The whole point of using Gauss's law is to simplify your problems, and we can make this easier by choosing a surface that has area vectors that are parallel with our E field. Remember, an area vector is the vector that's normal to the surface, and so the vector that's normal to that tiny surface there is going to be pointing outward like so. And notice that it's parallel with our E field, and so that dot product just disappears. And then that simplifies this whole problem. So keeping that in mind, I'm going to rewrite my integral here as the integral of EVA, and now I can pull my E out because E is constant through that surface, and I end up with the integral of dA, and that just simplifies to EA. And A is just going to be the surface area of a spherical shell. That's going to be our Gaussian surface for this. Right, and so knowing that, now one other thing we got to consider is that this equation for Gauss's law works for free space and vacuums, because we have this epsilon naught here is the permittivity of free space, but we're inside of some type of dielectric material that has its own permittivities, being epsilon R1 and epsilon R2, and we need to consider those. So instead of finding the E field for this, we're going to find the D field, and the D field is given by the definition of epsilon naught epsilon R times E. And this, when we plug this into Gauss's law, D changes our Gauss law a little bit. So instead of EA, we're going to get DA. And that's going to be equal to Q free instead of Q enclosed over epsilon naught. I don't need to include my epsilon naught because it's already written into D. And my Q free is similar to Q enclosed, but they're not the same thing. And Q free, we can find Q free in the same way that you would find the mass of an object given its density, because the mass is given by, if you know the density, you can multiply it by its volume and it'll tell you what its mass is. But instead of mass, we're trying to find the charge. Luckily, we're given a charge density for this problem, and we can use that charge density and multiply it by the volume of this region here that encompasses the radiuses from 0 to A. And if we do that, we can solve this problem, or we can find what Q free is. So we're going to need to take a volume integral for this. So we need to say that the volume integral of rho times dV. Now we can simplify this even further by breaking up my volume integral to dA and dr. Now dA is similar to what we did for our Gaussian surface. We can pull out the rho and the dA because they're both constant. And we're also keeping in mind that we're going from the regions from 0, where our radius is changing from 0 to r. So I can rewrite this integral as 0 to r. I'm going to rewrite rho as alpha. My dA is just the surface area of a sphere, and times dr. And when I finish this part of the equation, or when I do take this integral, I just wind up getting that we get that the Q free is equal to 4 pi r squared, r cubed rather, divided by 3 times alpha. Right, and I'm going to write that over on this, in this corner over here, alpha 4 pi r cubed all over 3. And we're actually done with this part of the equation. We have what we need for the first region, and we could go on to the second region, but let's just finish this problem. Let's just find the E field for this so we can get the hang of using our Gauss law. So, knowing what Q free is, I can rewrite my equation with dA, and I'm going to say dA, and I'm going to rewrite A as the surface area of our Gaussian surface, which is 4 pi r squared, and that is going to be set equal to our Q free, which is alpha 4 pi r squared cubed, and we set that all over 3. And you can see our 4 pi r squared cancels out with this part, and we're just left with alpha times r over 3. And now we can rewrite our d as how it's defined here, which is epsilon naught epsilon r1 times our E field. And when I solve for E1 here, and so this is our E1, and this is E2, and this isn't a vector yet. That's going to be equal to, E1 equals to alpha r all over 3 times epsilon naught epsilon r1. Okay, and that is the E field for our first region. Now, when we're in the second region, we are going to use our Q free. This is going to be important. This equation we boxed over there. So we want to keep that Q free present, and we're going to step over to a different slide. And okay, and so we're going to say we're going to do the same thing we did with the last problem. We're still working with the D field, so we're going to say D2 times our Gaussian surface is going to be equal to the enclosed charged, which was alpha 4 pi r cubed over 3, and we want to keep in mind that we're going to be finding what Q free is for some radius out over here, some arbitrary radius, but we have to incorporate this part of our equation, and so this part is represented by the Q free that we found here all the way out to radius A. So instead of having r cubed for this, we're going to plug in our A cubed. And so this is the Q free for the second region. Say region 2 is equal to alpha 4 pi 4 pi A cubed all over 3. And then we're going to find what the Q free is for our second region, and we're going to tack that on to this. And so we're going to do that in the same method that we used for the previous, for region 1. And so we're taking the integral of rho 2 times dV, and then so let's just focus on this. Let's just focus on this equation here. So this can be given by the rho 2 is given by this rho, negative beta r. So we say negative beta r times dA, which is 4 pi r squared dr. And it's important to remember your bounds for this. We're going from A, right? That's where we finished off our last region. And we're heading out to some arbitrary radius r. And when you take this, the negative beta and the 4 pi can all be pulled out of the problem. And we get negative 4 pi beta times the integral of r cubed dr. And that's going to equal negative 4 pi beta r to the 4th all over 4. 4's cancel. We end up getting negative pi beta r to the 4th. And we plug in our bounds. Remember that this is going from A to R. A to R. So I'm going to rewrite this as r to the 4th minus a to the 4th. Okay, so that is our Q free for our second region. And now I'm set to go back and rewrite the total Q free for the second region on the right side of our Gauss's law equation. So Q free 2 is equal to D2A, and that's equal to alpha 4 pi A cubed all over 3 minus beta pi r to the 4th minus a to the 4th. Okay, and that's equal to our D2 times our area, which is actually just another Gaussian surface, which is still a spherical shell. So we say 4 pi r squared. And now we can divide by 4 pi r squared and find out what D2 is. And remember, D2 is actually just our epsilon naught times epsilon R2 times E for the second region, and that is going to be equal to our Q free divided by 4 pi r squared. So I'm going to write that out, and I get alpha A cubed over 3 r squared. And that is and minus beta, pi's cancel out. I get r to the fourth minus a to the fourth divided by 4 r squared. And finally, we can find E2. E2 is given by alpha A cubed all over 3 epsilon naught epsilon R 2 r squared minus beta r to the fourth minus a to the fourth all over 4 epsilon naught epsilon R2. Make that a little bit more clear. Epsilon R2 times r squared. And yes, that is your E field for the second region, the magnitude of it. And we are done with our problem. Hopefully that was helpful for you. Thanks for watching, and good luck with your classes. Take care.